Okay, everybody, welcome back. Again, at the beginning, as we're going to be talking about a lot of different lipid molecules today, I just want to point out that we're not about memorizing structures here, but rather understanding the relationship between structure and function. So I'm never going to ask you which of the following molecules is phosphatidylcholine, because I've got better things to do than that, and you've got better things to do than memorize that. But I might ask you some things about whether you would expect a particular fat or oil to be solid at room temperature or not, based on whether or not it had double bonds. So again, focus on the application of what you've learned so far in OChem to the structured properties and functions of these biomolecules. Then a little bit later today, we're going to get to what's called terpene chemistry, which is comes out of the biosynthetic pathway that we use to make cholesterol and other steroids. But actually, lots of plants make all kinds of elaborate structures through this method. And the chemistry is pretty straightforward to understand, though the complexity of the structures made will blow your mind. If you get nervous at six-membered rings, you better hold on, because there's going to be a ton. But once you understand the principles, it's easy to work through, and that will be a part where we'll do some mechanisms. So, phospholipids. These are components of lipid bilayers and membranes, which, if you think about it, membranes are really important because they separate what is you from what is not you. And even within the cellular environment, you have membranes that separate particular compartments of the cell, different reaction vessels, as you, if you can think about it that way, and that allows a lot of diverse chemistry to happen. So let's talk about the basic structure of a phospholipid. It's basically the same as a triglyceride, only one of the three OH groups on glycerol is bonded to something that's not a fatty acid. So this can be a long hydrocarbon chain. This can be another long hydrocarbon chain. They don't have to be identical. And then in the phospholipid, you have a phosphate group attached to the oxygen of glycerol. And then, depending on what the R group is, that will change the properties of the phospholipid. I'll point out that if you have well, it doesn't even matter. Once you turn one of this OH group into a phosphoester, this carbon becomes a stereocenter, and it usually has R configuration. That would be controlled by the enzyme, not particularly important. And then depending on what the R group is here, that will change the properties of the lipid. So in some cases, R is, in some cases R is nothing. So your phospholipid would have two negatively charged oxygens on it. And if that's sort of the basic, basic lipid without bells and whistles, and that's called phosphatidic acid, or PA. People that do lipid chemistry often abbreviate lipid names, and so you may hear people talk about this in the various labs that you're working in. In contrast, if R is, I want to back up just a little bit. You guys know that phosphoric acid is like this, right? You guys know that like acetic acid or a carboxylic acid looks like that. You know that carboxylic acids can react with alcohols to give you esters, right? Similarly, phosphoric acid can react with an OR group. And whether or not these protons are there, there's pKa's that determine the first one is usually gone and the second one is somewhere between 10 and 50% gone at physiological pH. This is called a phosphoester, and I will usually draw phosphoesters with negative charges on both oxygens because that is a form that is accessible at physiological pH. But if you have two OR groups, that's called a phosphodiester. Okay, and this is something that a carboxylic acid ester can't do. It can't be bonded to two alcohol groups, but the phosphate group can be bonded to two alcohol groups. So maybe it'd be better for us to just put R here so that we can represent what each of the alcohols that forms the phosphodiester is. So in the case of our phosphoacylglycerol or our phospholipid, glycerol is one of the two alcohols attached to the phosphoester, and then this is the other one. So if it's just an OH group, you've got phosphatidic acid. If instead your alcohol is this, ethanolamine, then in the phospholipid it would look like this. And this would be called phosphatidyl-ethanolamine. And the interesting, people abbreviate this as PE. The interesting feature here is that once you add the ethanolamine to the phosphoester here, the whole head group becomes neutral. It's a zwitterion. It has a positive charge and a negative charge. And I don't know if you remember a couple lectures ago, we were talking about antimicrobial peptides and being attracted to the negatively charged bacterial membrane. Depending on how much eukaryotic cells have depending on the lipid composition of eukaryotic cells, those antimicrobial peptides don't bond or associate with the head groups of eukaryotic cells because, unlike phosphatidic acid, they are neutral. So there's another variant of phosphatidyl-ethanolamine. This is where the R group it's still the same basic structure, only the nitrogen is methylated, trimethylated, so it has to be positively charged. There's no longer any issues with pKa. It's a quaternary ammonium, and so within the lipid, you'd have something like that. And again, it's zwitterionic. This is phosphatidylcholine because that's what this alcohol, or that's what this particular amino alcohol is called. And then in some cases, the alcohol can actually be a serine, an amino acid. And how does the cell decide which lipids are going to be components of the membrane? I don't know. I can tell you, though, a little bit about fatty acid biosynthesis, which is involved in making the triglycerides. It's the precursor to this kind of thing. So if the serine alcohol were attached to the phosphate group, this is what you would have. And phosphatidylserine should have a net negative charge. So this lipid is called phosphatidylserine. So the lipids have the same basic structure with fatty acids. They just differ in the identity of the head group. And membranes in different cell types will have slightly different lipid compositions. The outer leaflet of the lipid bilayer will sometimes have different composition than the inner leaflet of the lipid bilayer. People will typically represent phospholipids as having a polar head group with a circle, and then nonpolar tails, which are these little squiggly lines. And that's basically how people are going to represent those in future textbooks. But I want you to have the idea in your head that you sort of remember what the atoms are there, okay? Questions about phospholipids? General principle, what's the difference between a phospholipid and a detergent? A detergent is like a soap. A fatty acid would be an example of a detergent. The difference is the number of tails, right? A single fatty acid, say if you had the carboxylic acid group, and then, oh, do I dare? Nope, I really don't. I've got to draw. This is an example of a detergent. And if you look at sort of its general shape, it sort of has a conical shape. And so soaps and detergents form micelles because they, mice? No, it's micelles. There you go. Because the conical shape creates a lot of curvature, and so when these detergents associate with each other, they put their polar head groups on the surface of the micelle, and then they put the nonpolar tails interior, and it's that conical shape that allows them to form this kind of spherical structure. In contrast, the phospholipids, because of their two tails, are more cylindrical in shape, and I think we talked about this before, but what that means is when they self-associate, you have, I love copy and paste, it's so cool. They associate side to side, and because of their cylindrical shape, there's not a lot of curvature to that arrangement, and so the way that they bury their nonpolar tails is to have one leaflet like this associate with another leaflet, with their nonpolar tails like that, and then you have the lipid bilayer. So shape, it's a simple matter. It's sort of like Legos or Tinker Toys. You guys know Tinker Toys? That was a thing of my early childhood, so maybe even not. It's kind of a bummer when you have one of the Tinker Toy sticks and you break it off actually inside the little thing, and then you can't use it anymore. Sorry, go ahead.
Could they associate with the polar head group together?
Could they associate the other way? Okay, let's see if we can do this. The other alternative I think you're thinking about is this one. Whoa. And the answer depends on the solvent, right? If you're in water, you want to bury the nonpolar stuff from water, so this is the arrangement. Though, if you're in organic phase, or organic solution, you might imagine maybe that could happen. I don't actually know. But because everything here is water, we want to sequester the nonpolar stuff away from water, and so that's why we have the particular arrangement. But what I was saying, the Tinker Toy analogy or Lego analogy is just that shape determines how things assemble and what structure you can use. If you follow the Lego Masters with Will Arnett on Hulu, is it, or something like that, they're big on this technique called studs not on top, called snot. And this is where you adjust the Lego pieces so that you can have more of a three-dimensional structure. If you want to come to my office and see an example of that technique, you can see my lovely Star Wars helmet things on my desk. But anyway, shape determines structure and function, right? Okay, anything else you want to ask about lipids? Or phospholipids, rather? Yes?
What exactly is the difference between fatty acid and phospholipid? Is it only the number of chains?
The fatty acid is just the carboxylic acid with the long chain. The lipid, the triglyceride and the phospholipid is that long hydrocarbon chain is attached here, but it's forming an ester with one of the oxygens of glycerol. So in your phospholipid, we could have drawn what these groups are. Going to sort of run out of space, but the fatty acid is the long hydrocarbon tail. And I'm not counting what these are, but we're trying to keep them sort of even numbered. Yeah. Okay, others? Okay, so that's your membranes. There's another component of membranes that you'll hear about. Again, this is purely for you to see and have seen the structure. But there's a class of lipids called sphingomyelins, and this is a sort of an independent solution to the idea of making a lipid bilayer. The structure is entirely different, but it basically does the same thing because it adopts the same shape. So here is a strange amino alcohol. Do we have to memorize the structure? No. And the structure is shown in your text. So if you don't want to copy it down, you don't have to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, did it. So this is an amino alcohol called sphingosine. And if you take this OH group, so we'll just highlight the sphingosine part in pink. If you take the OH group of sphingosine, the primary OH group, and then make a phosphoester out of it. Sure. Ooh, did I draw that right? And then put ethanolamine on it. You again have a nonpolar tail and a polar head group. And usually, the amino group also gets modified as an amide with a long chain hydrocarbon. We won't sort of worry about how many atoms there are there. So the core of the sphingosine molecule that is synthesized is right here. And then because it already comes with a long hydrocarbon tail, then you only need to add one fatty acid to the molecule. And then you've got the polar head group here, which is very much the same as phosphatidylethanolamin. And so this will have, again, that same basic shape that we expect of a phospholipid. It'll have two nonpolar tails and a polar head group, same sort of cylindrical shape. So this can be in bilayers too. And the name sort of indicates that it's found a lot in the cells that make the myelin sheaths around neurons, which is why it has the myelin name in it. Okay, so do you need to memorize that structure? No, but I would hope if you would look at it, you could see the analogy to a phospholipid and be comfortable expecting that to be in a membrane. All right. Okay. So that's it for membranes. That is our brief tour of membranes. There is a bunch of stuff in the chapter about fat-soluble vitamins, which are included in lipids. And any of you that are interested in that, go ahead and have a look. I don't really see the need to draw the structures for you here. Give that a read so that you know at least sort of globally what vitamin A and vitamin D, vitamin E, and vitamin K look like, and be able to understand, looking at their structures, why they're fat soluble because they're so nonpolar. We will come back to vitamin D a little bit later because we are going to talk about how you make it from cholesterol. It involves a really cool photochemical reaction, and we'll save that for the very end of the class. But I think I won't spend any time today talking about that. Clearly, I'm not going to say which of the following is vitamin A, which of the following is vitamin D, but if you were to see their structures, you would hopefully be able to recognize why they are soluble in organic solvents and well, fat soluble, meaning they can be stored along with triglycerides in your adipocytes. Okay, there's another section in the text about what are called icosanoids, and again, I don't want this to be draw complicated molecule day just for the purposes of doing it, but it's sort of worth talking about. So, icosanoids are made from a 20-carbon fatty acid. And it's called arachidonic acid, or sometimes icosanoic acid. And it's got 4 double bonds in it. And we don't necessarily need to know the structure of arachidonic acid. The chemistry about how this linear chain of 20 carbons gets functionalized into something that's quite complicated. It's all very interesting. Nevertheless, we're not going to have time for it. But I do want to show you some structures of some of these molecules. The types of molecules that are in this class, and they come from this linear 20-carbon fatty acid with 4 double bonds in it, are the prostaglandins. So you've heard about those maybe before. What do? Anybody know? What's that? Sensitize pain. They're related to inflammation. Some prostaglandins lower blood pressure and inhibit aggregation. Some stimulate uterine contractions. Some lower gastric secretions. There are leukotrienes, which have 3 double bonds conjugated to each other. These are involved in constricting smooth muscle in lungs. And so some of the asthma drugs are related to, I think, leukotriene synthesis or inhibiting their action. There's another class called thromboxanes, which is kind of cool. And these are related to triggering platelet aggregation. And then there are prostacyclins, which are related to dilating blood vessels and inhibiting platelet aggregation. So lots of different functions. You can see the offsetting functions of platelet aggregation triggering versus inhibition. That's important because you don't want your blood to clot, except when you actually want it to clot. So I just want to show you the structure of a particular prostaglandin so you have an idea of what to expect. It involves a 5-membered ring. You've got 2 OH groups, and then you've got the following 2 sort of mostly nonpolar tails. So that's one of the chains, and then the other is here. You have an allylic alcohol. And this is called prostaglandin F2 alpha. And there's lots of different prostaglandins that vary in structure, functional groups, and so on. But this idea of a 5-membered ring with 2 sort of tails and it's 20 carbons long is typical of the prostaglandins. So there's an interesting story, actually. It's a BYU story, so we should definitely talk about it. There for a while was known only one enzyme that catalyzed the formation catalyze one of the reactions of in prostaglandin biosynthesis, and this is called a cyclooxygenase, which should make sense. In the idea that there should be something named that way is that you have this 20 carbon unsaturated fatty acid, and then suddenly there's oxygens everywhere, and there's a ring. So cyclooxygenase is going to do some oxidation, and it's going to do the cyclization reaction. And this enzyme is inhibited by the non-steroidal anti-inflammatory drugs like aspirin and ibuprofen and so on. And you can go to the protein data bank and you can sort of search for COX-1 in complex with aspirin, and you'll see exactly how aspirin blocks the synthesis of the prostaglandins. It ends up blocking a tunnel that the molecule needs to get through. But in the late 80s, Professor Dan Simmons, who was a biochemistry professor here in our department, discovered a second cyclooxygenase enzyme, and discovered the gene for it and discovered its function. And it turned out that this was also related to pain, and in fact that inhibiting this enzyme could create relief for some chronic inflammatory arthritis conditions that were not well addressed with the NSAIDs. And so at the time, it was fairly new. The Human Genome Project wasn't yet complete. The idea of patenting a gene was not really something anybody did. And so BYU didn't patent the gene, though it entered into an agreement with a company that was going to develop inhibitors. That company was later bought by Pfizer, and Pfizer developed the drug Celebrex. There were a few of them. Celebrex, Vioxx was, I think, Merck's drug, but these were powerful pain, what do I want to call it? Anyway, painkillers, especially for arthritis. And Pfizer made a ton of money off of this. BYU later sued Pfizer for a violation of a license agreement and ended up recovering a substantial portion of the profits from Celebrex. And a lot of that money has now gone to fund the Simmons Center for Cancer Research here on BYU. Any of you doing undergraduate research in the chemistry department have, in many cases, the chance to get paid to do your work. And that money is in a large measure comes from the settlement with Pfizer. So we have Professor Dan Simmons to thank for that interesting discovery, and it continues to bless BYU. The terms of the settlement were not disclosed, but if you're really interested, Pfizer took a fairly substantial write-down in their profit margin when the settlement occurred, and you can go figure out what it was and do the math. So, okay. But anyway, Professor Simmons was the one that taught. I had him as a professor when I was here, and he's really great and been a great friend of the department. He's now retired, but we continue to benefit from that discovery. Okay, so prostaglandins. Now, interesting chemistry. So I'm trying to figure out whether we should just start with the horrible things and go from there. And I think the answer is yes, we should start with horrible things. Okay, I'm going to draw for you a few natural products that you may have heard about. And then we're going to talk about where they come from. Ah, yes, here we go. This is fun. Are you afraid? I'm not afraid. Yeah, so it's not actually that bad, but take Master Yoda's warning to heart. There's a particular molecule, six-membered ring. Ooh, I told you. It looks like this, and this is called limonene. And this is an essential oil that's found in citrus. Kind of smells lemony, which is why it's called limonene. You can take the same basic core structure and modify it a little bit. And I'm not showing stereochemistry here because we're focusing on connectivity. This is called menthol. And you can isolate that from peppermint, among other sources. A related molecule that does not have a double bond, does not have a ring, a six-membered ring, is this aldehyde. And this is called citral, and it's found in lemongrass. Let's see, this particular one is called geraniol. And it's found in roses. Oh, you're going to love this one. This one is a bicyclic ring system. It starts looking like limonene, only there's a four-membered ring in there with two methyl groups. That's called alpha-pinene. Like, what the heck? The best way to think of this is to draw a chair. Sort of looks like this. Okay, so it's a bicyclic ring system. You've got the six-membered ring here. Then you've got a four-membered ring, 1, 2, 3, four-membered ring there. This is found in pine trees, and if you've ever worked with turpentine, alpha-pinene is a major component of that. The double bond can sometimes be here, and if that's the case, it's beta-pinene. So those probably don't look at all related to you. But there are some interesting patterns. First, I want you to notice that all of them have these branching methyl groups, these methyl groups that come off of tertiary carbons. There's one there, a couple there, branching methyl groups. Okay. So paying attention to those methyl groups is actually going to be pretty useful in terms of dealing with these molecules. So that's one thing to look for. The other thing to look for is number of carbons. And if we count in limonene, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. And actually all of these are 10 carbon molecules. And I will tell you that all of them come from a single precursor, a single common precursor. And this is called geranyl pyrophosphate. It's like geraniol, only the OH has been replaced with the pyrophosphate group, which is an excellent leaving group. Okay? So somehow we're going to learn how to take this starting material, and actually even simpler ones, and convert them into some of these structures. Now I want to give you a little bit of background before we jump into the mechanism of formation of these things. These molecules are called, in general as a class, are called terpenes. And but they are composed of what we will call isoprene units. What do we mean by that? Goodness sakes. Well, isoprene is the following 5-carbon diene, and I'm going to choose to number the atoms 1, 2, 3, 4, 5, even though that's probably non-IUPAC numbering. That's the branching methyl group we're going to call 3. And this is an isoprene unit, and the general structure of terpenes involves, without sort of worrying about the double bonds or the oxygens or wherever, this is the basic sigma framework of an isoprene or of a terpene. You've got a 5-carbon unit with a branching methyl group on carbon 3. So, and in a terpene, each carbon is part of one and only one isoprene unit. Identifying isoprene units is the key to seeing how these things were synthesized. So let me show you how you can do this. First, you look for the branching methyl group. So let's take geranyl pyrophosphate, and we'll call the branching methyl group 3. Okay, then the one that it's bonded to is 2. And then I find in most terpenes, I'm going to find a unit that has 2 methyl groups attached to carbon 2. This is sort of the tail of the molecule. And that methyl group will be 1. Once I find that, then 1, 2, 3, 4, 5, and that's 1 isoprene unit. And then I know that this bond must be the bond between 2 different isoprene units. So I'm going to label this first one, I'm just going to highlight it in pink or whatever color I want. And then notice that atom 5 of 1 isoprene unit is bonded to atom 1 of another isoprene unit, 1, 2, 3, 4, 5. Now, sometimes the double bonds will still be there between 2 and 4. Other times they won't, but this basic sigma framework is going to stay the same. 1, 2, 3, 4, 5, bond between isoprene units. 1, 2, 3, 4, 5. And then you've got a leaving group on carbon 5. So this molecule has 2 isoprene units, which we will label like this. Okay. You get the idea? Start with the branching methyl group, and then try to identify which carbons belong to which isoprene unit, and then which bonds, in this case, a sigma bond between 5 and 1, are the things that connect the isoprene units. Go ahead.
So for the purposes, is 5 always going to bind on 1?
Yes, 5 is always going to be bound to 1. Maybe other stuff too, because there's other stuff that can happen afterwards, but that's the starting framework. Because as I said, each of these complicated molecules I get from this precursor, and so I'm not going to remake that bond. I'm going to use that in the precursor. We are going to learn where this comes from, but we'll start with the isoprene units. So let's dig in with limonene and see if we can identify the isoprene units. So right away, I'm going to try to find branching methyl groups and call them carbon 3. Then the tertiary carbon that 3 is bonded to, we'll call 2. And then I'm going to look for the tail, the fish tail of the molecule where there are 2 methyls, the 2-methyl tail. And though it's got a double bond, I'm going to ignore that and just realize that this likely came from the tail of my precursor, so I'm going to call that carbon 1. 1, 2, 3, then this one should be 4. Now at this stage, I may not be sure what to do. I could choose to call this carbon carbon 1, and this carbon carbon 5, and then this would be the bond between them. But I think you can see how I could also call this carbon 5 and this carbon 1 and have this be the bond between them. So at this stage, we don't know. There's a couple of possibilities, though I happen to know what the answer is. And so I will show you what it is, but if you were identifying isoprene units, I certainly would not count that alternative as incorrect, okay? So here's one. Once you decide which carbon is 5, then the thing it's bonded to is carbon 1, and then you see if that fits. 1, 2, branching methyl group 3, 4, 5. Okay, and then I'll highlight the second isoprene unit. So now I can see, first, I can see that this sigma bond between 5 and 1 was in the linear precursor. Had to be. But now I see a bond that wasn't, right? This sigma bond between 4 of 1 isoprene unit and 5, that's new. We had to make that. Okay? Questions about identifying isoprene units? Yeah?
So, I guess I just missed it. What was the logic in determining which one was in the linear precursor and which one was? Was that just from how you named it, and you said, well, if I name this that? Talking about bonds.
Which bond was in the linear precursor? Yeah. Once you decide what the isoprene units are, the bonds between isoprene units, between 5 and 1, those were in the linear precursor. Yeah. Other questions? Yeah.
So, does it matter, like, in that first unit, the double bond was between 1 and 2, and then
Yeah.
the second one, it was between 2 and 4. Does it matter, like, where that double bond is?
No, we're going to ignore the double bonds for the purposes of identifying isoprene units. The reason you can have that variation is because we're going to have a carbocationic intermediate with different kinds of beta protons, and so we'll have the opportunity to do eliminations, E1 type reactions from different adjacent carbons, and so that will be how we get the variation where the double bonds are. So this is going to actually go back to some 351 chemistry. Other questions? Let's do alpha pinene since that one looks scary. I think based on what we've done here, you could do menthol. And I think based on what we did here, you could easily do citral and geraniol. But let's do alpha pinene. Again, I'm going to look for branching methyl groups attached to tertiary carbons. And then second, I'm going to look for the double methyl tail, and that's right here. So this would be carbon 2, and then this would be carbon 1. Now I got to try out a few things. 1, 2, 3. If I go here and call this 4, then either one of these has to be 5, right? Not sure which. So in order to see which works or whether if the options are reasonable or not, I remember that 5 has to be bonded to 1. So I'm going to ask myself, could this be carbon 1? Well, it's bonded to carbon 2, so maybe. All right. How about over here? If this is carbon 5, could this be carbon 1? Is it in the right place to be bonded to carbon 2? Yep. So we've got 2 possibilities for identifying isoprene units, and that's okay that you can't tell the difference between them. We know that one of them is this. This is the sort of tail. And then as to whether we should go this way or this way, it actually won't matter. Because along the way, we probably go through a symmetric intermediate. So let's just go ahead and choose carbon 5 on the left. to be part of our isoprene unit, and then let's see if it works out. 1, 2, 3, 4, 5. Now, I know you are uncomfortable with ambiguity. I know you do not like it that we got to a point where we could have assigned the isoprene units in 2 different ways. If it follows the pattern, I can't call it wrong, all right? And we're going to see actually later on how you get how you get alpha-pinene from this limonene precursor. And so some of the decisions I made here about what the isoprene units are related to the decisions I made here and are related to my knowledge of the biosynthesis. Again, I know you're uncomfortable with the fact that I called this 5 and this 1 instead of going the other way. If you choose to go the other way, it works out just fine. Don't worry about it. Okay? Questions? Now, weird way of talking about things. Molecules that have 2 isoprene units. Remember, an isoprene unit is 5 carbons. So these 10 carbon terpenes have 2 isoprene units. Get that right. 2 isoprene units. And if you have 2 isoprene units, oddly enough, you are called a monoterpene. I got nothing there. So terpenes are molecules that are composed of isoprene units. They will have numbers of carbons that are multiples of 5. If you have 2 isoprene units, for whatever reason, you're a monoterpene. I'm now going to show you the structure of a sesquiterpene, which has 3 isoprene units. Do I dare? Yes, I do dare. I feel like Yzma in The Emperor's New Groove. I bet you weren't expecting this. That is such a good movie, man. That came out when Amber and I were dating, and we just watched it all the time. To this day, we can quote it, and couple of my proudest Papa moments were when my children quoted it in appropriate situations. Like at one point, we thought something was burning in the oven, and I said, do I smell something burning? And Nate said, my spinach puffs! And I was like, yes! And then there were other times where Dallin would say, the line, a llama, he's supposed to be dead. And Kronk says, yeah, weird. And so little Dallin was, yeah, weird. So just great moments. Anyway, this has nothing to do with Yzma. That is a sesquiterpene. 15 carbons. Sesqua means 1.5. So how do you even start on that? What you do in an exam before now is you look at that, you stress about it, you look at the answers and see whether by process of elimination you can eliminate anything. You get down to 2 answers. If you're lucky, one of them's the right answer, but you think and you think and you think, and then you get tired and then you choose the wrong answer, which is how it goes. So you got to calm down and focus on what you know. Let's identify the branching methyl groups. 3, 3, 3. The carbons they are bonded to should be carbon 2. And then I'm going to look for the double methyl tail. Where is it? Right here. Okay. So your assignment, should you choose to accept it, or even if you choose not to accept it, you still have to do it, is to figure out where the isoprene units are in here. And we'll talk about it next time.